Yeah, okay. Good evening, all. Okay, let's start. So now 3-4 days are remaining to your final exam. So I think you have already prepared all the topics. And today I have some sample or practice question for week 6 to week 8. So I'm just sharing the peer deck with you, and we will revise the topic using these questions. First, I will ask the answer from you, then we will discuss the solution. So we will discuss the concept also. After that, if you have any query in any particular topic, any in between in this question discussion, so you can also ask. Can anyone confirm I'm audible or not?
Yes, sir, you are audible.
Yes,
Sir,
Yeah.
one general query I have. How many questions will be there in written exam?
30 questions.
30 questions.
Yeah, 30 question, 90 minutes. Okay. The exam duration is I think 90 minutes, so total 30 questions are there. So average time for the each question is 3 minutes.
What will be the level of difficulty for the question?
Yeah, so some questions are easy, some questions may be difficult, so yeah, it can be managed. Okay, I'm sharing the peer deck with you. So take paper and pen also if you require. So some question are maybe the use of paper pen. So just try to solve each question in 3 to 4 minutes. Okay, so that is the average time for your final exam also. Yeah, first join the peer deck session using this. I'm also sending the link in chat box. Join the session on peer deck. I have shared the link in chat box. So please participate, all the participants. So total 28 participants are with me on the live session. So please join all and reply on each question. Yeah, once again, I have sent the link in chat box. So those who have joined just in few minutes, you can use the link, and you can also use the link which I shared in our screen. So out of the 31 till now, only 13 students have connected. What about others? Just try to solve. If you are getting the correct solution, that is fine. Otherwise, you can learn also, because the questions are the similar level of your exams. Okay. Okay, so now 17 students have connected. Okay, I'm just starting now. Yeah, others we still not join, please join. Now 20 is fine. Okay. Okay, I'm just starting the first question. So just try to solve within 3 or 4 minutes. After that, we will discuss the solution. So yeah, this is the first question. So I have 5 questions from each week. So week 6, week 7, week 8. So total 15 questions I have. So now the first question is related to week 6, and the topic is concept is make heap concept. If we perform the following operation on the max heap, so this is the actually max heap is given in the list, then the resulting max heap would be after 3 operations. Okay, so we are performing these operations sequentially. First we will perform the delete max operation. Okay, then we will again repeat this operation delete max. After that we will insert the 30 in our max heap. So what should be the final max heap? This is the, I think similar, this there is one similar question we have already asked in quiz 2, I think. Yeah. So out of 21, 3 have a response. Okay. So I have started this question of 7, 9. Oh, sorry, 7, 7. Now, so we will discuss on 7, 12. Nice. 8 have responded. So those are joined late. I'm just sending the link to join this periodic session and response. Give your response on each question. Okay, now so now in 5 minutes I have received 16 response. Now I am just showing the response. Okay, so 13 have marked D, answer D, and 3 have marked answer C, and 1 have marked B. Okay, 0 for A. Okay, 17. Who is the Lux? Lux, can you turn off your video? Okay. Yeah. So the most of the students, most of you have replied the answer D. Okay. Now just check how we are calculating the solution for that. Okay. So this is the question given for him. I have also no answer key for that 15 questions. So I have also tried. Okay. Now 30. First we create the max heap. 30, 20, then 25, and then 5, 15, and 23, then 10, then 3, then 2. Okay, so we can simply created the tree just using the label order. First start from the root and then the left child, right child, and top down manner. So we will just create that max heap using this given list. After that, we will perform the delete max operation. So we will just swapping the max element in by the last element. Okay. So after swapping these elements, what will be the max heap? So we will just swap the element to 20, 25, and 5, and 15. Yeah, 15, and then 23, then 10, or then 3, then so okay. After swapping, we will remove the max element, and then we will create max heap again. Okay, so what will be the max heap now? After swapping and removing the last element. So after swapping the max element to the last element, we will remove that from the list. Then we will create max heap again. Okay, so now who is the max element in these three elements? 25. Okay, so we will this 25 will come at the top. 25, then 20. Now this is come here. 5, then 15, then 3, and now this 2 will be shifted by the maximum element. This so this 2 will come here at the one step, then this will come here. Okay, so 23 will be shifted above, and this 2 will come here. Okay, so after removing max element, so this will be the max heap. Now we will perform once again delete max. So we will swap this 25 by 3. Okay, so after that, what will be the next max heap? So 3 will come at top, 20, 23, and then 5, 15, and 2, and 10. Okay, so 25 we will remove. Then we will make max heap again. So which is the largest element in the top 3. Okay, so 23. Now 3 will come here, and 3 and 10. Then now 3 will come here, and 10 will move up, and this will move up. Okay, so now 20 will 23 will come at the top position. 20. Now 5 and 15. Then now 10, 2, and 3. Okay, now the last operation is insert 30. So we will insert from the last position. So we will insert at here 30. Now this 30 can be moved up only. So 30 will move here, and 5 come here. Now once again 20 is also less than this 30. So this 30 once again move to the top, and 20 will come here. Then now 30 is also greater than 23, so 30 will move here and 23 will be shift here. So in the final version of the max heap will be, so 30 will come at the top, 23 will become the left child, this will be remain the same 3, and this 20 will come here, 15 will remain at the same position, and this 5 will come here. Okay, just write down the sequence. So 30, 23, 10, 20, 15, 2, 3, and 5. So okay, so 30, 23, 10, 20, and 15, 2, 3, 5. Okay, so the answer is the D. Okay, is anything, is there any questions, or I'm just sharing the next question? Okay. This is the next second question from week 6. So there is no option for that, just input your answer. There is one term is used in for that question. A binary search tree in which every node has either 0 or 2 children is referred to as a strictly binary tree. Okay, so this is so we call binary tree as a strict binary tree if every node have either 0 or 2 children. This is the one definition. So what are the number of internal nodes for a tree with 42 leaves? So leaves is the last node which have 0 child. So what are the internal nodes? So nodes which so the remaining nodes other than the leaves nodes are called the internal nodes. So yeah, there are some property are related to the binary tree. So you should also learn this property. So sometimes this question is root also internal node? Yes. So we consider root as also a internal node. So for this type of question, if you never listen this, never learn this type of property, so you can simply observe these property by taking some examples. Okay, so
Excuse me, sir.
Yeah.
So what did you say? Root is internal node or not?
Root is an internal node.
Okay. Thank you.
So total 47 participants are there. Only 25 joined this peer deck session. Other can also join and respond your answer. Link for the joining this session. Once again I have pasted in the chat box. You can use the link which I have pasted in the chat box just now. Yeah, so out of 25, 18 have responded. Okay, nice. Okay, so I'm just explaining the solution. Oh, 61, yeah. So this is 39. Okay,
I guess so you can change this view.
change. Oh, now this is fine. But I'm not able to check how many students we have to count this. And why the number is not so? Okay, so yeah, 41, 41, 41. Okay, 1, 3, 4, 5, 6, 6. So 6 students have responded as a 41 answer. 39. Other than that, 63, 63, 86, 86, 61. So 63 is also a common answer. Okay. And the remaining are very less. So 73, 64, 40. Okay. So can anyone can anyone tell me why the 63 you are thinking about that part? The 63 is the answer.
Yes, sir.
So how you
So, sir,
calculate
it is.
the 63 answer?
Sir, the question is telling that there are 42 leaves.
Yeah.
So, uh, if we take the 2 to the power 6, then we will get 64. And if we take 2 to the power 5, we will get 32. So technically, we are at the 6th level.
No, no. So the question is that there is one binary search tree which every node has either 0 or 2
Either 0
children.
or 2 children.
This is
Yes.
the one condition is given. After
Yes.
that, we are asking that the number of internal nodes for a tree with 42 leaves are.
Hmm.
If
So for 40,
if any tree have 42 leaves, so what are the internal nodes in that tree? Okay. So if you take some example, for example, one second. Okay, this is the same question. Yeah. So for example, if you create a simple strict binary tree, okay, so there is one node I have created. So this is not a strict binary tree because here this is the node which have only one child. So this is not a condition for a strict binary tree. Okay, so I'm just creating a one strict binary tree. Okay, now this is strict binary tree. I am also can add here. This is
Yes,
also
sir.
strict binary tree. Okay. So after that, you can observe that how many internal nodes are, how many leaves are. in this tree. Okay, so 1, 1, 2, 3, 4, 5, 6. These are leaves. After that, other than that, how many internal nodes are there? So you can count 1, 2, 3, 4, 5. Okay, so you can take 2, 3 more examples. So for example, if you just create like that, this is also a strict binary. So now you if you count the leaf node, so 1, 2, 3, 4. So there are 4 leaf nodes, and how many are the internal nodes? 1, 2, 3. So there is one property in a binary tree. So if the number of leaves node in strict binary tree is n, so the internal node will always be n minus 1. Okay, so answer will be 41 for that.
Actually, sir, I try to configure that one.
Yeah, so most of the time we count the root as an internal.
Oh, that is why my answer is coming 40.
40.
It is 40. Okay.
Excuse me, sir.
Yeah.
But it is nowhere mentioned that the given leaves are leaf nodes.
Given?
The given 42 leaves. Okay,
Yeah,
okay,
it is
sir.
given.
Got it.
Yeah, that is given. So number of internal nodes for a tree with 42 leaves. So this is the part is given. Okay. Is it clear to all?
No, sir.
Yes, sir.
No, sir. So this is actually a property of strict binary. So if tree have if in a tree if each node have 0 or 2 children, so in that case the leaf node is always one more than the internal node. So you can take any example of this type of strict binary, then definitely the leaves will always be one greater than of the internal nodes.
Sir, I have a doubt in this question.
Yeah.
But, I got the answer 41. Okay, but
Okay.
now when you draw the graphs that are in the right side, the bigger graphs. After that, I was thinking that it would be also possible, and I think the internal node should be asked as the maximum internal node possible, right?
Maximum internal node. Okay.
After that we can got the conclusion that 41 nodes should be in internal nodes. Otherwise, in this question, that in the right hand side, that means the graph, that in if there are 42 leaves here, then we can't conclude that there are 41 internal nodes, right?
No, definitely if any tree which have 42 leaves, then definitely 41 will be the internal node.
So is it true for only strict binary tree?
Yes. So is it this is the property of this strict binary tree, basically. If you create a binary tree of which have 42 leaves, definitely the 41 will be the internal node.
Yeah. And sir, is there any difference between strict binary tree and complete binary tree?
Yes, difference is there. So for example, if we create that,
complete binary tree will have strictly two nodes,
yeah,
2 child nodes.
so
for
this
every
is
node.
this is a complete binary, but this is not a strict binary.
Okay.
Okay, so if you see that the last node, before the last label, every label should be filled completely, and at the last label, so we can if we can visit the from the left to right, so before the last node added, every node should be added. So if for example, if we say that, so this is okay, so this is the last node added on the last label, so before that every node should be filled, no one can be skipped. So for example, if we skip that part, skip that node, so this will not remain the complete binary tree. So label, so we can say that in the label order should label wise order should be filled.
Heap is complete binary tree.
Sorry, your voice is breaking. Hello.
Heap is complete binary tree.
I am only able to listen complete binary tree. Before that, what are you saying? Can you repeat once again more?
Sir, is it a binary, like complete binary tree? Like, I think the complete binary should be like if we are at level 5, then the level should be completely filled. Then we call it. We can call it complete binary tree.
No. So last level. So there is no property is that the last level should be complete filled. Before the last level, every level should be filled, and on the last level, the last node before that, every node should be filled. There is one more category is also
full binary tree.
Yeah, full binary tree. So
Sir,
oh, okay, that is full binary tree. Yeah, actually, I got confused with it.
So this is a full binary tree actually. So we can say that every full binary is always a complete binary tree, but we cannot say that every complete binary is a full binary. Okay.
Okay, sir.
Hello.
Yeah. Hello.
Audible?
You are audible. Yes. Who is this?
Heap is a complete binary tree.
Sir, he is asking heap is a complete binary tree.
Heap. Yeah, heap is a complete binary tree.
And what you say on the full binary tree? Difference between full and strict?
Full and strict. No, I am just explaining the difference between full and complete. Okay, so this is a full binary tree and this is a complete binary tree. For example, if we added this one, so this is a complete binary tree. So sometimes we can say that every full binary tree is always a complete binary tree, but we cannot say that every complete binary tree is a full binary tree.
And full binary tree is also a strict one.
Yeah. This is a strict.
Sir, if you don't remember this property, then is there any way to make out?
Yeah, so I'm saying that you can take some example. You can observe this property by taking some examples. So just follow the property here. The property is given of a strict binary. Every node should have 0 or 2 children. So you can take some 2-3 example or 4-5 example and just observe the property if you are not remembering this.
Sir, one more thing I want to ask.
Sir?
Binary tree can have one node also, right? One child node also at the last.
In which one?
Means a complete binary tree can have one node also, right?
Yes. So this is a complete binary tree and there's only one child.
And the full binary tree have means either have 2 nodes or have 0 nodes.
No, so full binary tree means the level, all levels should be filled. So if we have started this level, next level, so this level should be filled for full binary.
Before leaf, all levels should be filled.
Yeah. Full means so these are the levels for level 0, level 1, level 2, level 3. So every level can maximum contain the 2 to the power 0. So this is 1, this is 2 to the power 1, maximum node are 2, 2 to the power 2, maximum nodes are 4. So this is the level property. So every level can contain maximum 2 to the power level number. Okay. So 3, that is 8. You can count these 3. Yeah. Any other question?
Sir?
Yes. Yes, Sika.
Sir, what if the leaves were 8 leaves? So could you draw the diagram? Sir, without the diagram, it is a little difficult. With diagram, it will be clear. Because sir, 42 leaves we cannot draw.
Yeah, so you are asking for the 8 leaves persons.
Yes, sir.
Okay. So this is also example of 8 leaves. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now you can count the internal nodes. 1, 2, 3, 4, 5, 6, 7. Okay. Or you can also count one
Yes,
like
sir. But
this.
sir, here all the last leaves turn out to be 8. There, uh, in case 2 to the power 3 is 8. But there, how 42 is not any number. We'll reach
No,
2
no,
to
no.
the power 5
So I am
32.
also drawing some another example. Okay, so just see this.
Okay, yes.
1, 2, 3, 4, 5, 6. Now see the leaves node. 1, 2, 3, 4, 5, 6, 7. Okay, one more is there.
But this is not a strict.
No. Now this is okay. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now total leaves are 8. And how many internal nodes are? 1, 2, 3, 4, 5, 6, 7. So we are talking about the binary search tree here, but we are not talking about the balanced things and complete things in this question. So we binary tree can be in any form. Okay, is it clear? Okay. Okay, now we will move to the next question. Okay, so this is the third question. Yeah, so now participants are 57 and in the PDX session only 26 have joined till now. I have pasted the link in the chat box. The remaining those are not joined, please join the session and respond the answer. Okay. So now 20 have responded for that question. I'm just showing the answer. Okay. So yeah. So this time receive the combined. So 11 have marked the D option. This is the most one. And no, it is checked. So do not change the option after showing the response from. Okay. Okay. Now 13 is the maximum response for D, and A, B is are 3 and C are 2. Okay. So what are the D option is? Okay. So 1, 3, 4, 5. So according to your response, so answer should be 1, 3, 4, and 5. So this is the 1, 3, 4, and 5. Okay. So first property, which of the following statement is true? So first property is that the smallest element in a max heap is always at a leaf node. Yeah, so this is a correct property. So if you draw any max heap, for example, if we are drawing 5, 4, 3, for example, 2, 1, or anything, so element can also be repeated. So always the smallest element will always come at the leaf node. Okay, so here the two options are similar. So in the first and second, here it is given as the at the lowest level, and this is the leaf node. Okay, so this is the difference. So for example, how we can prove that the option 2 is not correct? So 10, for example, 10. Here the element is 8. Okay, and so for example, yeah, this is also a this is
2 on right side.
Yeah, 2, and then you can do 5 and 3. Okay. So for example, if you are making this max heap, this is also a max heap, but the smallest element is at this position. So this is the level 0, this is level 1, this is level 2. Okay, so this property is not always true, but the smallest element always will come at the leaf position. Okay, if smallest element is not come at the leaf position, so that it will definitely it will violate the max heap condition. The next property is the second largest element in a max heap is always a child of the root node. Yeah, this is also true. If you see any max heap, so the first largest is always come at the root position, and second largest will always come at the child node of the root. So this property is also true. Deleting the smallest element in a max heap takes order of n times. So deleting the smallest element in a max heap takes n times. That means first you have to find out the smallest element, okay, in a max heap. So it will take actually order of n times. So finding the minimum element on a max heap, it will take the n times, because we cannot say that that the maximum heap always come at the lowest level, or there is no property. The lowest element can be come at any position. It can maybe come on the left part, or it may become on the right part. So we have to search all the elements to finding out the smallest element. So it will take order of n time. Okay, so this is also true. And the last property, finding an element in a max heap, takes order of n time. So if we are searching any element, it is exist or not in a max heap, so it will also take a order of n times. So because there is one property in max heap, so parent is always greater than the child node, but there is no property between left child or right child. So
it is equivalent to search in an array, basically.
Yeah. So it is similar to array. So there's no property between, there's no relation between the child's node. So because of that, so there is no order maintaining for the element. So we have to search, we have to search all elements to finding out the element, any particular element. So it will also take in order of n times. So yeah, 1, 3, 4, 5 is the correct properties.
Sir, why not 2?
Yeah, explain this example. You can see this example. The smallest element in a max heap is always at lowest level. So what are the lowest level for that is this one.
Leaf.
Not leaf, lowest level. So this is the level actually. This is first level. This is the second level.
Okay,
This
okay,
is the
right.
0th level.
Level.
This is the one, and this is the last level. So this is the lowest level actually. But you can see the smallest element is 2. This is not at the lowest level.
Okay, okay, got it. Thank you, sir.
Okay, let's move to the next question. Yeah. So this is the question which is related to the binary search. Okay, so 19 response I have received. Yeah, so this time got. So 18 have marked the answer C and 1 have marked the answer B. Okay, so just check that. C means A, B, C. Okay, yeah. So most of the marked answers 45 and 60. To just create the binary search tree using a given sequence, we know that we will insert element one by one in a empty binary search tree. So we will start from the 50, insert as a root. After that, we will insert we will insert 80. So we will always compare from the root node, and when we find out the empty location, then we will add. So if 80 is greater than 50, so we will add 80 here. Okay. Now 20, so 20 is less than the root, so we'll add here. Okay, now 60 is greater than 50 and less than 80, so it will come here. Now 10, so 10 is less than 50, less than 20, then come here. So okay, now 45, so 45 is less than 50, greater than 20. Okay, now 65 is greater than 50, less than 80, greater than 60. Okay, 65 and 30. So 30 is less than 50, greater than 20, and less than 45. Okay, so 30 will add it here. And 90, so 90 is greater than 50, greater than 80. So 90 location is found. Now 90 is added here. So we are asking that the elements which have only one child. Okay, so the elements which have only one child, this is the one and this is the second one. Okay, so now 45 and 60 is the answer. This is the correct one. Okay, good. So I'm just the next. Yeah, so this is the next one. This is also related a heap. And this is the last question from week 6.
Sir, can you explain this question once? Like, I'm not getting the question.
So which of the following is our possible elements in path from root to leaf in max heap? So for example, if you have a max heap, so which of the possible sequence of elements in the path from root to leaf? So I'm just explaining that.
You mean like if we go in binary tree on single path? So
Yeah,
that we
single
have to
path
tell
from
that.
root to leaf. Yeah. So for example, we have a max heap things. Okay. So if we are seeing this sequence from root to this one, okay. So what are the possible elements.
Okay, sir. Got it.
Okay. If any sequence, so from root to any leaf. Okay, so I have received the 20 response in the times. Okay, just saying. Yeah, so same things this time. The most of the response I have received C 20 and one I have received for A. Okay. So okay. So in that question we are asking the possible elements. So there is one relation in max heap. So always the child is in max heap, always the child node will be less than or equal to the parent nodes. So if we are traversing the root from root node to any leaf nodes, so there is one property. So we are comparing the parent node and child nodes. Okay. So from root node, the child node of the root node will be always be lesser or equal to the parent node. So this property we can check which option containing this property or not. So if you see the option 1, so 80, 33, 27, 24, 1, 13 and 10. So yeah, this is a decreasing order. Or we can say that the non ascending order symptoms is used. Yeah, so this property is filled. Now 80, 33, 33. So yeah, similar value can be possible because the parent value can be equal to the child value. Okay, so 33, 33, 24, 13, 10. Yeah, this is also a correct. 24, yes. And in third option, so 80, 33, 33, 24 and 27. So this is not a decreasing sequence. So after 21 we are getting the 27. That means the child node is 27 and the parent node is 24. This is not possible in max heap. So same things for the fourth option, 80, 33, 44, 44, 26. Yeah, same things. This is the child node and this is the parent node. So parent node cannot be less than the child node in max heap. So this is not correct. So 1 and 2.
But it can be equal because max heap means it should be greater only, no?
No. So I'm comparing this one, 24 and 26.
But in second option there is 33, 33. So
yeah, it is possible.
Node, okay.
Yeah, it is possible if you are creating, for example, 10, 10, 8, 5, 2, 4, 3. This is a correct max heap. Value can be repeated in max heap.
Okay.
Okay, so if you see the parent sequence, root to leaf node sequence, so 10, 10, 2. So value can be repeated. Okay, but the child value cannot be the greater than the parent value.
Sir,
Okay, so
one request from my side.
yeah.
It will be better if you can like keep the language of the expressive. Like I was not getting the language actually. What does it mean like from path root to leaf?
Path. Yeah, you don't know what is the meaning of path from root to leaf. So in tree we use the term root for the top node, and leaf is the last node which have zero child.
Yeah, like sir, if we can frame this question in such a way that if we start from root and follow a single path to any of the leaves in the max heap.
Maybe some language so you are feeling that, but the question is straightforward. So possible elements in path. So we are just considering the elements in path from root to leaf in a max heap. Okay. Okay. I'm moving to the next.
Sir,
Yes.
sir, if it would not have been max heap, instead it would have been binary search tree, then how would we have known which one is the correct answer for the last question?
No, so binary search tree, then this property, I think we have to check that. So for example, no, so binary search tree, the sequence can be in any order. So if you visit the right part of the, for example, this thing does 10 at 20, this is 5, 1, 2, okay. So this will 15, this is 35. So this is a binary search tree. So here this property will not be fulfilled. Okay, decreasing sequence or increasing. So if you traverse this part, so this is a decreasing sequence, but if you traverse the right part, then it is an increasing sequence. Or it may be some increasing and decreasing also. So this property is not fulfilled in the binary search tree.
So sir, this path is correct or incorrect?
So here we are talking about the max heap. In that question,
yes, sir, we are talking about the max heap.
Yes.
But my question is, if it would not have been max heap, it would have been binary search tree, then how we are checked? Because here we are checking that it should be decreasing sequence.
Yeah. So in max heap, we will get always the decreasing sequence, but in binary search tree, we can get any sequence, increasing, decreasing, or it may be a combination of both. So why are you applying this this decreasing property on binary search tree? This is question related to the max heap only. So in binary search tree, there is a property: the left child node is always be the less than, and the right child will always be the greater than the parent node. Okay, so this property cannot be fulfilled. But in the heap, max heap, child node is always will be the less than or equal to the parent. Because of that, this property is fulfilled.
So binary tree cannot have same element, right?
Binary tree is the different thing. So binary tree can be anything.
No, so but can it has like same element like 33 and 33 repeating elements?
You are talking about binary tree or binary search tree?
Binary search tree.
Yeah, binary search tree, we generally we did not store the same element 2 times. In binary search tree, we will not store the similar element 2 times repeatedly.
Okay, so thank you.
Okay, I think next question is also visible. So now this is related to the big 7. So if you have any doubt to understand any questions, so you can ask. Okay, so I have received 17 response for that. This time I've received the combination. So maximum 9. I marked the D answer. 3 mark the C, 1 mark the B, and 6 marks the A. So A and D are the confusing. Okay. So any of you marks the A option and D option. Okay. So just create the Avl tree for that. So Avl tree generally creates the balanced binary search tree. So we will start from the first node 8. Okay. After that, we will we will always insert the element in the binary search tree fashion. So 4 we will insert, 4 is less than 8, so we will insert on the left. So now there is no balancing affecting. So if we are finding out the slope, so the slope for that is 0, 0 minus 0, 0, and the slope for the 8 is 1 minus 0 is 1. So there is no unbalancing here. Now we will insert next element 1. So 8, 4, and 1. Okay. So now slope is 0, 1, and 2. Now we will apply the rotation for that. So we will apply the clockwise, and now 4 will come at the root position, 8 become a right child, and 1 become here. Okay, now slope is 0, 0, 0. Now next node is 3. So we will insert 3 in this tree. So 3 is less than 4 and greater than 1.
Sir, the slope for 4 is 0 because slope of the root is the sum of leaves, is it?
No, slope is calculated by the left height minus right height.
Right, okay. Okay.
Yes, okay. Left height is 0, right height is 0. So we just solve this. 0 minus 0 is 0. Here the left height is 1, the right height is 0. So 1 minus 0 is 1. Okay. So after that, we will add the 3 here. So now 4, 1. Now 3 is less than 4, greater than 1. So 3 will add here. 8. So slope for is 0. I'm just representing as the positive value. So this is 1, this is 0. So now this is 2 minus 1 is 1. So there is no unbalancing. Now we will add 9, 3, 9. Okay. So 4, 1, 3, and 9 is greater than 4 and greater than 8. Okay. Still 0, 0, now 1, 1, and 0. Okay. And now we will add 2. So we will add 2. So here 4, 1, 8, 9, and 3. So 2 is less than 4, greater than 1, and less than 3. Okay. So now this is come here. So this is 0, this is 1, now this is 0, this is 1, this is 2, and this is 3 minus 2 is 1. Okay, so now this is not a balance, so we will apply 2 rotation on that part. So first rotation will be apply on 3, and we will rotate this part as a clockwise. So after performing this rotation, and 1, this 2 will come here and 3 will come here. Now we will apply the second rotation on that part on the anti-clockwise. So it will come here 4, 8, 9, and it will come 2 here, 1 here, and 3 here. So 0, 0, 0, 0, 1, 0. Okay, and last element is
Sir, the root will be 1, right, in the last drawing?
No, there is one element remaining now, 11. Okay, so we will add.
No, sir, why has 4 been assigned a 0?
Where?
In the last tree, the balance tree.
0, because the left height is 2 and right height is also 2. So 2 minus 2 is 0.
And how are you calculating the height, sir?
So height, we generally calculate the longest path. We will check the longest path on the left side and just take the number of nodes.
And sir, how are you able to tell that the tree will require 2 rotations as soon as you saw it?
So actually, if you see the Avl topic, so there are 4 type of rotation we applied generally. So there are some, I've explained this LL rotation, RR rotation, and LR rotation, and RL rotation. So these are some 4 type of rotation we applied on the according to the condition. Okay, here we are actually, when we are, this is the condition RL type. Okay, so here we added the last node here. Okay, we are adding the last node is 2 here, and weight of the node become 2 for that node 1. So we will check that where is, so the right part now this time the right part of this node is the heaviest part. So because the height of the right part is 2 and the left part is 0. So we will check that we will move to the right side. So we will check, we will move to the right side children. So this is first called R. Then we check the where from this child node we added the last node. So we added the last node on the left side of that 3. Okay, so this become L. So this is the called RL rotation. So we applied this RL rotation. So in that case, we applied 2 type of rotation. First perform on the child node. This is clockwise. After that, we applied the rotation on that node which have slope 2. So this part. So we will get after 2 rotation this part.
Excuse me, sir.
Mhm.
So can you explain once again that how do we conclude that it will be R or L?
Okay, I'm just showing the all the type of rotation. Just wait. Rotation. Yeah. So first thing, if we will calculate the slope for every node. So this is the condition for the balancing or unbalancing things. So slope factor, or sometimes we call the balance factor. If the for balancing, the left subtree height minus right subtree height is always be less than the 2 for balancing. If this value is become 2 or more than, so that means the tree is not balanced. So we will apply the rotation, left rotation and right rotation. So there are some situation. These are the some situation. For example, element insert order 1 2 3. Okay, so we are inserting 1 2 3. So at the each time when we are inserting, we will calculate the slope for every node. Okay, so when we are inserting 1, so slope for this node is 1. Okay, so after that we are adding 2 in that tree, so we will calculate the slope also. So here we are calculating the actual value. So the height of the left part is 0, right part is 1. So 0 minus 1 is minus 1. Okay, so same thing for the next part. So we are adding here. So now the balance factor is become minus 2. Okay, so when this value is become 2 or minus 2, so we will apply the rotation. So for this type of situation is called RR rotation. Okay, so in that case we applied the 1 rotation on that node which have 2 slope. If we see the absolute value of the slope, so this is a 2, we will apply the left rotation on that node. So after apply the left rotation part, so we will get this right side diagram. So next, second type of situation, right rotation, 3 2 1. If we are adding the node in that fashion, so 3 now 2 is the left child of 3, now 1 is the left child of 2. So this is, in that case we will get the 2 slope on 3 node. So same things, we will apply the right rotation, sometimes called clockwise rotation on that node which have a slope 2. So we will get this balance tree. So this is the second type. This is the third type, right left rotation. Okay, so if we are getting this situation, for example, we are adding 1, we are adding 3 as the right child of the 1, then 2 as the left child of the 3. So this type of situation called the left right rotation. So in that case we apply the 2 rotation. First of the right child of that node which have slope 2. So we will apply the first rotation of node which have value 3. So we will apply the right rotation on that. So after that we will apply the left rotation on the node which have slope 2. So we will get this final one. Same for the reverse side, left right rotation. So these 4 type of rotation we applied when our tree become unbalanced. Okay. So things, yeah. So there is one remaining element 11 is there, so 11 we will add, so that 4, 2, 1, 3, 8, 9, and 11 will come here. So now balance back slope is 0, 0, 0, 0, 1, 2, and this is 2, now 1. Okay, now so this part have become unbalanced. So this is called the RR situation. So we will apply anti-clockwise rotation on that part only. So 4, 2, 1, 3, and 9 will come at here, 8 will come at here, and 11 will come at here. Okay, so this becoming Avl tree. So 1, 3, 8, 11, 1, 3, 8, 11 is the answer. Okay, we are moving to the next. Yeah. This is the next question for related to the Hookman algorithms.
Okay, sir.
Yeah.
So can we have that slides PDF?
Slides PDF for?
Which you were showing that summary of Avl tree.
This one? Yeah, this is the this is the link which is available on GitHub. You can see the summary. I'm just sharing with in the chat box if you don't have.
Okay, sir.
So all 10 big summaries are available. Okay, so I will. This is the 7th person. So here we are asking for the length of. Okay, so which of the following are the correct length of the codes for the character set A, B, C, D, E, F for the given frequency. Okay, after calculating the codes, check the length of the each code. Okay, so I received 13 response for that question. So now see the most of the response for D, 11, and 1 for B and C. Okay. So just create a Hoopman tree for the given frequency. So we will select the minimum 2 value. So first is 2 and second is 6. Okay, and create the Hoopman tree for that. So just represent that in the rectangle box, 2 and 6. Okay, now it becomes 8. So 2 is representing for the E and 6 is representing for the C. Now we have 8 and the remaining ones. Now 8 is the minimum and next one minimum is 11. Okay, so we will just consider that 11 for F and create a Hoopman tree. Now it become a 19. Okay, now next one, 2 minimum is 13 and 13 and 19. So we will keep as here 13. So A, this is 32. Okay, now next two small is 30 and 35. 30 or 32. Okay, so now we will consider as here 30. This is for B and it becomes 62. And now next is 35. So okay, 35, it is for D, it become a 97. So what are the length for A, B, C, D, E, F? So A length is, so you can count the edge. So if you mark 0, 1, 0, 1, 0, 1, 0, 1. So where is A? So A is 1, 1, 0. Okay, 1, 0. This is length 3. B is 1, 0. This length 2. C is where is C? This one. So 1, 1, 1, 0, 1. 1, 1, 1, 0, 1. Length is 5. Now D. D is here. So length is only 0 and length is 1. And E. So this is at the lowest level. 1, 1, 1, 0, 0. So 1, 1, 1, 0, 0. Length is 5 and F is here. So 1, 1, 1, 1. This is 4. So 3, 2, 5, 3, 2, 5. So D 3, 2, 5 and 1, 5, 4. Yeah, 1, 5. Yeah, D is the correct answer for that. So there is also one property. So every code generated by the Hoopman tree is always a prefix code. We call the prefix codes, but the condition is that no one code is come at the prefix for others. So if you see the code of for B 10, so it will not come as a prefix for any other codes. Okay, so this is the property is contained by the Hoopman codes. So next question is, this is related to greedy algorithms, interval scheduling. Okay, so I've received 14 response for that. Now see the 4, 4, 3, 4, 4. Most of the answer is 4. And 3 is also available. 3, 3, 3, 4 times 3. And 1 is, yeah, okay. So 4, maximum answer is 4. Okay, see that how we can solve this problem. So first we arrange the activity according to the ending time. Okay, this is the problem based on the interval scheduling. So we will arrange the activity according to the ending time. So for example, this which one is the smallest? This is the 5. Okay, yeah. So 2 to 5 is the first one. Next is 3 to 5. And okay, now 5 is completed. Next greater is 7. Okay, so 4 to 7. And this is 2 to 7. And next one is 8. So 6 to 8. Yeah. 6 to 8. And next one is the 9. So 6 to 9 and 8 to 9. This is covered. Now next one is the 10, 7 to 10, and one more 7 to 10, and next is 12, 9 to 12, and 10 to 14. Now we will just mark that activity. So we will take first activity, and we can start the next activity at the same time of the finishing of the previous activity or afterward. So we are finishing here 5, so we cannot start this activity, cannot start this activity, cannot start this one also. We can start this one. Okay, 6 to 8. Now finishing time is 8, so we cannot start this one, but we can start this one. Okay, 8 to 9. Yeah, so now next is 7. We cannot start. Now we can start this one. Yeah, so after this we cannot start this. So we can perform maximum 4 activities. Yes, so 4 is the correct answer for that. So yeah, this is the next question. This is based on the minimum lateness. Minimize the maximum lateness.
Sir,
Yes.
So the time starting from 0 second or for 1 second? What to assume?
0.
Okay.
For that question, so calculate the lateness for each activity and just return the maximum value of the lateness. Okay, so 12 response I have received now. 1 1 1 3 1. Okay, so most of the answer is 1 and 1 is 3. Okay, just see the solution for that. So these are the activity given here. The question, first we will sort the activity according to the deadline. So we will arrange the activity according to the deadline in increasing order. So 6 is the smallest, so 1 3 6. Next is 8, so 3 1 8, and next is 9. Okay, so 2 2 9 and 4 4 9. Next is 5 3 14 and 6 2 15. Okay, so we have arranged the activity according to the deadline, and we will just start from the 0 timing. So this is the 0, then we will complete it at first activity on the time 3. So now the deadline for this activity is 6, so there is no lateness, so lateness will be 0, and we will start from 3. The next process time is 1, so we will complete this one. This is the third activity at the 4 times. So now deadline is 8, we have completed before that, so now lateness is 0. Now we just start the next one, this is 2, so we'll complete it at 6.
Sir, can you repeat
Sorry, repeat.
Can you repeat that step, the second?
Okay. Yeah. So first step is we will sort the activities according to the deadline in increasing order. After that, we will start from the timing 0. Okay. So this is the process time to complete the activity. So if we are starting from 0, so we will complete this activity at time 3. Okay. Now the deadline for this activity is 6, so we have completed before that. So now the lateness will be 0, and we will start the next activity at 3. Now the next process time is only 1, so after adding 3 plus 1, we will complete it at 4. So now this activity is completed at 4. Now the deadline is 8, so we have completed before that, so now lateness will remain the 0. Now next activity process time is 2, so we are starting from 4, so it will be completed at 6. Okay, now the deadline is 9, we have completed before that, now the lateness is 0. Now we are starting next activity 4, adding 4 here, so now we have completed at 10. So now the lateness, so we have completed at 10, but the deadline is 9, so there is one lateness value will be 1. Okay, 10 minus 9 is 1. Now we will start next activity. So for example, 10 plus 3 13. Okay, so now the deadline for that is 14, so we have completed before the deadline, so lateness will be 0. Now next process time is 2, so that is 15. This is also 15, so we have completed at the same time of the deadline, so it will remain the 0. So the maximum value of these all lateness is 1. This is the answer.
Sir, in case all the other processes we do at time before deadline or at the deadline, and the thing where we are late by 1 unit, if we are late by 2 units, so the minimized maximum lateness would be 2.
Now, for example, the value of this activity is 2, this is 5. Okay, so we will select the maximum value, so this 5 will be returned. Actually, we are minimize the maximum lateness.
I guess we have to sum them up and then return the answer.
Sum
So
of
he's
all
asking,
lateness.
yeah.
No. In that case, if we have two similar type of similar timing activity, so that sum will be some can be changed. Some of the all lateness can be different. If we are just, for example, so for that case, okay. So here the deadline are same. If we are change the order of these two activities, so some will some maybe change for the for this swap, but the maximum lateness will remain the same.
Sir, as like for a final answer, what will we have to return?
The maximum value of all lateness. So in that case, the all lateness was 0.0.0.1.0.0. So what is the maximum value in all that? So this is the maximum value.
Okay, sir.
Sir.
Yeah.
So when the deadlines, then the two deadlines are same, then how will we sort them? On which basis?
So for example, if you reverse this part, so 9, okay. So answers will remain the same actually, but in some cases, if you are adding the all lateness value, so these value can be changed after swapping this deadline.
So
you
when we need to add this, at what type of condition we have to add all the lateness?
If in any question, if we are asking that what is the sum of all lateness is, so in that case you have to return the sum. But here,
in that case, the order also will be defined.
Yeah. So if so, for example, if two activity have the same deadline, so answer can be the different. Two answer are possible for that case.
Excuse me, sir.
Yes.
So for the hypothetical lateness which you wrote over there, 5 to 1, among them, how will we decide that what will be the minimized maximum lateness?
5 to 1. So we will return this 5 value. Maximum lateness. So what are the maximum lateness is in among all these lateness? So this is the maximum lateness, but this is the minimized value actually.
Using this algorithm, we are minimizing and then returning the maximum.
Yes. Using this algorithm, this maximum value is the minimized maximum value. Otherwise, if you arrange the activity in random order, so this maximum value can be more than that.
So is there any specific name for this algorithm?
Yeah, minimum lateness. Minimum lateness, sir explained in the week 7. Greedy algorithm, interval scheduling, and then minimize lateness. We are actually minimize the lateness of activities. Minimize lateness or minimum lateness. So there are some names we call. Okay. Okay, so we are not total. Now this is the 10th question. Just this is also a Hoopman based question. So which of the following is not a valid encoded message for a given Hoopman tree? So there is one Hoopman tree is given. So there are 5 letters used in the given Hoopman tree. And this is the encoded message using these Hoopman codes generated by this Hoopman tree. So which of the following is not a valid encoded message? Okay, so 14 response I have received. So now the D answer we have received by 12. Okay, it is correct. So here the encoded message is given, so we can verify this using the Hoopman tree. We will just traverse the tree according to given message. We'll just start from the left to right person and take the digit one by one. So we can mark on that. So 0 0 we can traverse. We will always traverse from the root. When we reach at the leaf, we will move once again on the root. We will repeat this process until we just finish the message bits. Okay, so 0 0. Now this part have been completed. Now 0 1. Okay, this part have been completed. 0 1, and next 0 1. Same things. Okay. Now 1 0. 1 0. Okay, completed. Now 1 1 1. At this part we have reached at the leaf. Now 1 1 0. Okay, so we have reached at leaf. Now 1 1 1 completed. Now 1 0. Okay, so this is the correct one. We will check for the next one is so 1 0 1 0. Yeah, first part is completed. Now 1 1 1. Okay, we will reset the leaf here. Now 1 1 0. Now 1 0. This part is finished. Now 0 0. Okay. Now once again 0 0. Now 0 1 and 1 0. Okay. So we have complete finish. Same for the next. So we will repeat this process. Now we are checking for directly D. So 1 0. 1 0. Yeah, this is the leaf. Now 1 1 1. This is the leaf. Now 1 1 0. This is the leaf. Now 0 1 0 1. This is the leaf point, and 0 1 and 0 1 1 once again. Now 1 1 1. So 1 1 1 completed at here. Now we remains one extra one. So in that case, we can move only till here. So this is not the valid encoded message. Other than that, all are the valid. Yeah, okay. Yeah, Arjia, Datta. Yeah, correct. Extra one is there. Okay, now move to the next. So now this is the week 7 is completed. Now the question has come from the week 8. So this is the 11th question, which is from the week 8. Okay, now the answer 6. So 2, I have received 7 and 4, and other than that, most of the answer are 6. Okay, so we can directly count the inversion using the cross point. Okay, so we are not calculating the every situation, so you can just write the sequence 1 in increasing order first. So 1, 2, 5, 6, 7, and you can write the same sequence 2, 7, 6, 1, and 5, and just match the all value, and just this one 7, yeah, this 7, this is 6, and this is 5. Okay, and just count the cross point. So 1, 2, 3, 4, 5, and 6. So this is the shortcut method to count. So answer is 6 for that. Okay. And the next question is 12th question. Okay, so now this time 14 have marked as the C answer. Okay. Yeah. So the brute force complexities for the closest pair problem is big on n square, and the next is the divide and conquer technique is complexities and log n. So 1 and 4 is the answer. Is C. So this is the okay. The next question is 13. Okay, so 12. Oh, now this time is the combined option I've received. 2, 6, 2, 3. So B have the most of the answer is 6. Okay. B. Yeah. So what is the B answer is 2, 3, A, 2, B, 3. Yeah. So yeah, B is the correct answer. You can observe these things. So for example, if you see the recurrence relation for D, so this is the similar for the binary search we used. So every time where we are reducing the size by half, such by the half, and each time the complexity is 1. Okay, so we can the complexity of that part will be log n time. Okay, so we are discarding the half of the input every time. Also D is the link for the 1. Okay, so we have 3 of them there. Now next one is the Tn equal to Tn minus 1 plus n. Okay, so here this is related to the, if you see the complexity of quicksort in worst case. Okay, so if you remember that, so if we are reducing one element to recalling the algorithm again, and each time we are taking order of n times. So the complexity will be n into, so this is the part n, we will start, so the total number of label will be n here. So if we draw the tree for that, 13. So yeah, for example, for the C option, if we draw the tree, so we are starting from Tn. Now we will move to the Tn minus 1, and every time we are taking what we go of n. Okay, so n times. Same for Tn minus 2, order of n. So this height will be remain the n, and each time we are taking order of n, so total complexity will be n square. So this links to the this part, and these two are basically related to the so here if you see we are dividing the equal partition, so we are starting
Sir, for the
yes,
previous case, how did you say that it was n square? I don't understand.
so we are starting from the problem with the n inputs, okay,
Right.
and each time we are taking order of n times extra.
Okay, right.
Okay, so this is the n time. So second time we will call the Tn minus 1. So this will be the n minus 1 because of n minus 1 basically. Okay, so I'm just not representing order of. So this is the n time, this is n minus 1 time, this is n minus 2 time. If you will add these all these things, so n plus n minus 1 plus n minus 2, then it becomes n square.
Right.
If you add this series. For this part, so if you we are starting from Tn, so Tn by 4, Tn by 4, Tn by 4, and Tn by 4. We are dividing in that way. Okay, if you are adding these all these elements, so it becoming n. Okay, so n by 4 plus n by 4 plus n by 4 plus n by 4, it becoming n. Same we will repeat on next level. So there is one property discussed in the week 8. where you can directly observe the complexity. Yeah, so this is a recursion tree. So if the input size is decreasing, so we can directly return the complexities Tn equal to order of Fn. If the size is remain the equal at each level, so we will directly return the complexities log n. Okay, and so here complexity will be Fn log n. Okay, and if the value is increasing at the each level, so we will calculate the complexity using this formula. So here the input sizes remain the same at each level. Okay, so here n plus 4 plus n plus 4 plus n plus 4 plus n plus 4 equal to n. So here is n, the at the same time here is also n. So value is equal, so we will directly return the complexity Fn, so log n. Here Fn is given like this, order of n, so n log n. Okay, so this is now this one, and here the value is decreasing. Okay, we are starting from Tn, so we are just dividing Tn by 8 and Tn by 8. Okay, so now value is decreasing, so if you see the n by 8 by plus n by 8, so it becomes n by 4. So we are starting from the n. At the second level, the number of input are become decreasing, so n by 4. So in that case, the complexity will be Fn. So what is the Fn is order of n. So it will remain the
Sir, in case of that Tn is equal to Tn minus 1 plus order of n, in that case also your Tn minus 1 is decreasing, but in rate is very low.
Yeah, so here we are dividing on the equal partition, so like this, in that way, so like a tree form, but here this is not a tree actually. Here we are just decrease one value for our input, so this is not created any tree like that.
Actually, yeah, that the number 3 is not a recurrence tree, that is why we can't apply. Okay.
Yeah. Okay, so not 2 questions remaining, just discuss. Yeah, next is 14. Okay, so yeah, this is just no calculation is required for that question. Yeah, I'm just showing the answer. Oh, still. Yeah. So for E option, we received the 6 response. D option, I have also received the 3, and A, B, C 1. Okay. So maximum response for the E. So for that question, yeah, MOM, you have already learned this median of medians algorithm. So when this median of medians algorithm find out the median element in order of n times. So after using this algorithm, so finding the kth largest element, we can find out this kth largest element in order of n times. So this is true. And quicksort complexity in worst case also can be decreases as a n log n time using this finding the median of median algorithms. So 1 and 3 option is correct. No, 1 second. Yes, so 1 and 3 is correct.
Yes, sir. 1, 2.
Yeah, so 1 and 3 option D is correct. So why we received most of the response E. Okay. So you should remember these things in the summary. Recursion tree, find, yeah, select. Yeah, these things. Selection become order of n in fast selection algorithm using this MOM algorithm. Quicksort becomes L log n using MOM. So this is the next thing. And next one is the last person. Yeah, 50.
Sir, in this question, MOM is always, if I want to select the pivot through MOM, it is always divide this 3/5 and 3/10 and 7/10.
Not this is the approx condition.
I am telling you approx. If I apply the MOM, it will always take that interval 3/10 and 7/10.
Yes, I think in lectures have discussed these things. For the this this integer multiplication. Yeah, this is MOM. Oh, yeah, the median of block median lies between 3. Yeah, so this sir have proved this part. This is the drawing part, the brown color. So median will always come at this position. We are selecting this blue part. So all the brown elements will always be the less than. So this is the third part of the. Okay, so median will always lies between 3rd and 7th.
Okay.
Part. Okay, so now this is the last question. This is simple. Just identify the algorithms, which approach we are used.
March short. Is divided by 5p.
So, sir, can we expect these types of questions in end-term exam?
Yeah, so you have already given 2 quiz and 1 mock. You have also given in 1 mock. So yeah, definitely you get the idea.
Okay, sir.
Yeah. So question will be based on the same concept we have discussed. We cannot say that the exact question. Okay, so for last question, I've received the 14 response, and still 4 I have received for C, 9 for B, 1 for A and D. So B and C. So we are confused B and C. So 1A to, yeah. So first Prim's algorithm is. Is there anything wrong? Okay, now this is fine. Yeah, Prim's algorithm is greedy. Huffman code is greedy, and merge sort is a divide and conquer. Interval scheduling is greedy. and closest pair of point is a divide and conquer. So 3 and 5 should be related to B. So 3 and 5, yeah, B, and other than that, A. So B is the correct answer. So 2B, those marks for the C. So 2B. So Huffman code is not a divide and conquer algorithm. It is a greedy algorithm actually. We always select the 2 minimum element and then just create the 3. Okay. So I have finished these questions. Which, if you have any other question, then you can ask now.
So this week 8, this integer multiplication, there is one bit shifting. Sir, will you please discuss that part?
Bit shifting, integer multiplications. And where is this? Yeah, this algorithm, Karatsuba.
No, not exactly. I am asking Karatsuba, but the bit shifting part, if it is in decimal in other base, then how you shift that base?
Opening the slides, lecture slides. Yes. So this is the slides for integer multiplication. You are asking from here integer multiplication.
So go down, go down. No.
Which part?
Yes, sir. This part.
Okay. So this is the Karatsuba algorithm. So which part you are asking?
This bit shifting. Yes, sir.
So this is in the 2 to the power m. Okay. Okay, this is 2 to the power m. 2 to the power. Actually, this algorithm is basically used for the binary representation. If we are multiplying the binary digits, so because of that we are using this 2 here. Okay, if we want to multiply the decimal number, so we will use the 10. So you can take any example for the binary multiplication, then you can observe that how this is working. How we are actually dividing this bit parts.
Oh, if I want to use the decimal part, this instead of 2 to the power m, I will write 10 to the power m.
Yes. So if you see the code here, so here we will actually use the 10 to the power everywhere in the code. Yeah, this is 10 to the power. This is 10 to the power. So this is representing actually the base of the digit multiplication digits. Okay, just apply that algorithm on the binary numbers for the multiplication, that you can observe the correct things.
Okay.
Okay, any?
Sir, the closest pair,
Yeah.
In the closest pair, while we are selecting the that interval, because in between delta band, the pair value, if you can just discuss that part.
Have you seen the implementation of this closest pair?
Yes, sir.
So this is the implementation of. So which part you are talking about?
While I am selecting, because the cross zone.
Yeah, cross
Because,
zone. Okay.
yeah, sir
Merging
said,
part.
sir said the 15 boxes, but
Yeah. So this 15 value actually selected by just the not the exact things. You can select the 12 also. This
that
is
part
the,
you just make it a little clear, sir, because that is because.
so this is the safe. This 15 is selected for the safe side only. So this is not the exact things. I have already shared some related documents related to this. So this 15 is selected just only for the safe side. Otherwise, you can also select the minimum value for that. So okay, I'm just sharing the slides for that also. Yeah, this region. So this one, no? Here, sir mentioned that the next 15. Actually, when after the computing the minimum distance on left part, after computing the minimum distance of right part, we will just check the closest value on the border lines. Okay, so this value 15 is selected just for the safer side. Actually, we are starting from the lower to down, lower, so from bottom to up manner when we compare the distance between each element across the cross line. So, for example, if so, now this is not running. 1 second. My other browser is visible to you?
No.
Yeah. So after finding the minimum distance on both part, we will finding out the elements which are closest to this border line. Okay, so after sorting this, so we will start from bottom to up. So for example, if we are selecting this, so we will find out the distance in other side. Okay, so there is one element here. There is one, so we will just check the 16. Actually, this 15 value is selected for the this region 1 2 3 4 5 6 7 8 12 13 14 15 16. Okay, so if we are for example, if we are searching that this point region, so we can search here. We can any node can at this place, at this place also. So it can be possible that the 16 elements can be possible in this region. But I think I also feel this part. So we will never check the distance on the same region. We will always check the distance from the cross side region. If we are our point is on the left side, so we will always check the distance on the right part of this border. Okay, so yeah, because we have already calculated the distance on the left part. Yes. Okay. So we will always calculate the distance all on the right part. So the right part So there are possible region are 1, 2, 3, 4, 5, 6, like that, 7, 8, maximum 7, 8 or. So still I've shared the one reference on the discourse. This reference is related to any one book. So in this book, the author have already written that this 15 value is selected only for the safer side. Otherwise, we can select the less value. No need to require the compare the distance for next 15 elements. According to
So
me.
this 15 points, when we are telling, actually there is 15 box that we are referring. This 15
no, but 15 box is also not possible, because this distance is delta by 2. Okay.
Yeah.
This distance is delta by 2. So this complete distance is delta. Okay. So if you feel that this distance, there are 2 points on each node, each box. So then this is the violation of the value of delta.
No, 2 point in one box, it's not possible.
Yeah. In one box is the 2 points in one box is not possible. Also the all 16 boxes, the 2 points are not possible. Or so for example, if you mark that 1, 2, 3, 4, 5, 6, 7, 8, this is also not possible. If you take these 8 points on each box, so that definitely it will violate the delta value. So because this delta value is selected the minimum value which we have find on the left side or right side, the minimum distance between 2 points. So this delta is represented.
Why when we are checking this means boxes means distance from the point we want to measure the minimum distance, on that point we will check both sides, downwards and upwards both, or shall we check since we are start checking from the bottom?
So in our algorithm we are starting from the bottom nodes, so we will always the upper side
go up.
So we will never check the bottom side also.
We go up and the opposite side only, because this side is not required.
Yeah, this side is not required. So this 15 value, I think it is not required, but maybe this algorithm is discovered many before here. So at that time, so they think on the different levels.
Okay. Sir. Thank you.
Okay. Yeah, any other questions?
Hello, sir.
Hello.
Hello.
Yes.
For the interim examination, the most of the part will come from 9 to 12.
No, this is the So I have already posted 2 or 3 times on the discourse. The syllabus is week 1 to 11. Still, some students are posted that week 9 to 11 is the major part.
No, the syllabus is from week 1 to 12, but I was asking the most of the questions will come from every part.
No. Equal weightage.
It's equal weightage. Okay.
Yeah, equal weightage. Don't skip any weeks. End term. Yeah. Okay. Any other questions?
So the equal weightage thing is the case for all subjects or just PDSA?
No, I'm not talking about any other subjects. I'm just talking about the PDSA. You can ask the subject course related inspector to these things. I think for end term is always the syllabus is complete all weeks for all the subjects. Okay, so there is no query. Should we close? Okay, so bye everyone. Thank you.
So tomorrow we have one more session, right?
Yeah. So 2 to 4. So we will discuss the week 9 to 11. Okay.